Okay, well, good evening. I'm pleased to see, in spite of it being unseasonably cold, we have a good local audience in the hall, and I'm sure we have a large number online to hear a talk on an amazing area of engineering and science that has done wonderful things and has huge opportunities for the future. And we're really delighted that Professor Alberto Vecchio, who's a professor of astrophysics and director of the Institute for Gravitational Wave Astronomy at Birmingham, has driven over from Birmingham this evening to tell us about how it all works and how what was seen as an impossibly difficult experiment is now has that prospect of being another branch of astronomy. It's a remarkable story with much that's come far and will go further still. So Professor Vecchio, thank you very much.
Right. Okay. Wonderful. So first of all, thank you so much for the invitation. It's great to be here. It's great to be here in person. Actually, this is the very first talk I'm giving in person since the start of the pandemic, so I'm going to talk about the discovery of gravitational waves, what we've learned so far, and hopefully what is going to happen. Well, give you some hint about what may happen in the future. And just to make it absolutely clear, this is a talk for a society for the application of science and research. This is a field which is really in fundamental physics and fundamental science. So there isn't anything yet that I can point you that says this is the specific new piece of physics that we have done that will translate into a major revolution for the broader society. But I think something that hopefully is going to come through my talk, the discovery of gravitational waves comes from really decades of work and synthesizing progress in physics, engineering, applied physics, theoretical physics, data analysis, that have all been put together in order to do this breakthrough. And as we push the boundaries, I'm sure in the future, some of the work that we do in this area will then feed back into other areas of physics, engineering, and hopefully society. So, I'm going to start just to make it clear about fundamental physics and Gedanken experiments. Let's assume you want to conduct the following experiment. You have 3 blocks of stuff, 3 bricks, and you decide that you want to measure the separation of these bricks, okay? And you think this is a dumb thing to do. You take a ruler and you make this measurement. And I may agree with you. However, I not only want to measure the relative separation of these bricks, but I want to do it to some extraordinary precision. So this is the level of precision at which I want to make this measurement. It's a small number for physicists, but of course, small or large doesn't mean anything if you do not compare it with something else. So for physicists, this is 10 to the minus 18 meters, or another way of quoting this number is to say that it is about 1,000th of the size of a proton, okay? And so you say, well, okay, you want to make this measurement is a kind of silly measurement first, and then it's a pretty tough measurement. If you think a bit more about what it means, the level of precision at which you want to make this measurement is about a factor of 1,000,000 smaller than the average motion of the individual atoms that constitute this piece of material. They are at some temperature, we all learn that atoms and molecules move, and they move by about a million times more than the level of precision at which you want to make this measurement. Also, these kind of blocks need to be somehow engineered, attached to the ground in some way. And as I walk here, or pace, you can sorry, it's the control. You can check by how much the ground shakes due simply to the fact that I move. And it moves by about 1 billion times more than the level of precision at which I want to make the measurement. So you may say, just that, you are starting with a kind of silly experiment. You want to make a measurement that is clearly impossible. So, get a life, maybe go to a shrink and do something else. Now, there is a reason why people started seriously about 50 years ago to think about making this measurement. And the reason is because of Einstein's theory of relativity. So I think we all know, the great triumph of the theory that was presented in almost, just over 100 years ago, so 1916. And the general idea is, there is a delay, okay. The general idea is of the theory is summarized by this famous quote by a famous physicist, John Wheeler, who started really to revive the theory in the 60s and 70s in the US, where he says that the theory means that space tells matter how to move and matter tells space how to curve. So the idea of the theory is that the Earth doesn't orbit around the sun because there is this force at a distance, Newton's force of gravity, that keeps the Earth attached to the sun, but really because there is mass and energy, space-time will be bent, and the Earth will go on a straight path, but simply because on a curved space, and therefore will orbit around the sun. So we all know of the power and success of this theory, but being a new theory, it's full of new predictions. And one of these predictions is the prediction of gravitational waves. Gravitational waves, just to be absolutely clear, is a fundamental prediction of Einstein's theory. You remove gravitational waves, the theory falls apart. If you think Einstein was wrong, so you don't quite trust Einstein's theory of general relativity, any reasonably decent theory of gravity will have gravitational waves as part of the theory. And as a sort of analogy in your head, I think everybody is familiar with Maxwell's theory of electromagnetism. In electromagnetism, we know that we take a charge, an electron, we shake an electron, a dipole, and we radiate electromagnetic waves. Exactly in the same way, in gravity, we take a charge of gravity, a mass, we shake it, we accelerate it. In this case, is quadrupole, and this motion will generate gravitational waves. So this is the sort of picture to have in mind. You take the typical system that you can have as a generator are two masses moving around each other. As they move around each other, they shake space and time because they are radiating gravitational waves. And these are waves that travel at the speed of light, essentially undisturbed throughout the cosmos. This is from a theoretical physics point of view. You can also think in a different way if you're thinking about the universe as this is a way for every single mass in the universe to tell all the other masses, what they are doing. It's a kind of broadcasting channel in the fabric of the universe. Therefore, if you are able to detect these gravitational waves, you have a way of capturing new information that are sent to you. Okay. Now, one thing that, so this is what the theory predicts. Einstein, the paper about gravitational waves is just 2 years after his theory of general relativity. There is the solution. There is waves are generated by, let's say, accelerating objects. Einstein himself says, okay, I'm a great guy. Here's the solution of my equations. This is the prediction. Forget about trying to detect these gravitational waves. And the reason is that the kind of perturbations of space and time, then even an extremely strong generator of gravitational waves, some very compact objects moving at high speed, relativistic velocity, these little tiny perturbations are really super tiny. Okay, and in fact, nobody works on gravitational waves. Nobody actually works in gravity and general relativity for 50 years. Really, everybody works on particle physics during those years. But in the 60s, there is a renaissance, the beginning of a renaissance of general relativity. There is this famous experiment of Paul Rupka about the gravitational redshift. And people start to think about whether there is a way of actually trying to build a device that may measure gravitational waves. And so if you want to measure a device, you need to try to understand the, at the conceptual level, what is the kind of effect that you want to measure. And the idea is sufficiently simple. Assume you take a ring of particles and assume that there is a gravitational wave that is propagating perpendicular to this ring of particles, which is a perfect circle. As these waves propagate through this ring of particles, they will stretch and squeeze space and time, stretching in one direction and squeezing in the opposite one as they travel through. So in other words, the Gedanken experiment is if you want to detect gravitational waves, take some particles, measure their relative separations. If there are gravitational waves passing by, their relative separation will change. The real problem, so hopefully my initial example of the different blocks of material starts to make sense. The real problem is that if you think about what could be strong within inverted commas sources of gravitational waves, you have just to consider the universe, extremely compact objects like black holes, and they would give, by the time these waves get to the Earth, an extremely tiny perturbation of this ring. And really this number that everybody has in mind, the order of magnitude is one need to make a measurement at the level of roughly 1,000th of the size of a proton. So this seems impossible. However, there is a very famous instrument in physics that is really designed to make extremely precise measurements of that you can convert in distance. That is an interferometer. And this is, this slab of concrete of this interferometer that was used at the end of the 19th century by Michelson and Morley to do the famous Michelson and Morley experiment. But now you need to, engineer a system which is much more sophisticated. And so the idea of this system is as follows, and really major advances in material science, in laser technology, in vacuum technology, in sensors that takes place in the 70s, 80s, and then 90s allows this idea to become a reality. So the idea is to use a laser beam, shine a laser light, and you through this beam splitter, and you have two end mirrors. As the laser light goes, travel through the paths, if the paths of the two arms are exactly, they don't change, these two laser beams get recombined here at the beam splitter. You can measure what is the intensity of light there. If you arrange it in such a way that there is no light coming through, then you will see just, dark intensity. But if the mirrors change by a very tiny amount their relative separation because of gravitational waves, the intensity of light is going to be modulated. And the intensity is directly proportional to what is the actual change in the relative separation, which turns out is directly proportional to the waves, the gravitational waves that are encountered. So the idea is to use light as a ruler. You are not going to make absolute measurements, but you just make relative measurements between the two arms, because the level of the signal, the changes in the arms that you're looking for, the level of the signal that you're looking for is so tiny, you want to play all the tricks you can in order to enhance your signal optically. Because the actual length or size of the change of length of the relative separation is proportional to the separation of the test masses. You want to build an instrument as large as possible, long arms. You want to isolate your system as much as you can. You would like, in principle, to have these masses being freely falling in space-time and being just affected by gravitational waves. And very importantly, you want to build at least two experiments, because if you want to tell the world that you have observed, on a kilometer-size instrument, changes of relative changes of distance of the order of 1,000th of the size of a proton, people won't believe you, and therefore you want to really see the effect in different locations. Okay, so it took several decades to build, if you want, this extremely sophisticated ruler, and actually two rulers. They are in the US. They're called LIGO, Laser Interferometer Gravitational Wave Observatory. One is located here in the swamps of Louisiana, just an hour and a half drive north of New Orleans. The other one is located in Washington State in this missed nuclear waste dump site of the Department of Energy for the US administration. So you can clearly see the L shape, where this is the central station where the beam splitter is sitting with all the lasers and so on. There are these long arms and the end corner stations with the end mirrors there. There is a similar instrument not identical in design, but sufficiently similar, which is done by initially a French-Italian consortium, and now there are many more European countries participating to this. The previous one is 4 kilometers in size. This is 3 kilometers, and this is near Pisa in Italy, and it's called Virgo. Just to give you a sense of what this is, so this is the Hanford site. So 4 kilometers, this is the arm length. So this is Churchill College, and this is Addenbrooke's Hospital. I haven't measured it precisely, but roughly speaking, so it's a healthy jog, you know, to go up and down these arms. This is the vacuum tubes where the laser beam will travel because you really want to have a high vacuum system and nothing that disturbs the path of the lasers. This is one of the tanks that will contain the different optics for the instrument. This is a terribly complicated optical table, which is used inside inside one of these tanks. This is one of the suspension systems. So these are the mirrors that get suspended through this extremely clever engineering system, so that the mirror, although it's attached to all the rest of the infrastructure and ultimately to the ground, behaves as much as possible as a free falling test mass. And this is another image of one of these mirrors being installed. So it took about 30 years to put together LIGO and about 1,000 people. And on the Saturday, the 12th, 2015, the instruments were almost ready to start operating. And essentially what you do is you are like a surfer on the, on the ocean of space-time, waiting for the perfect wave, okay? These are all sky monitor. There is a great advantage with respect to astronomers, well, real astronomers, that you do not have to wait for, for the night. You can observe, the entire sky all the time. You, however, pay a price, and I'll show you a few things in this respect, in the sense that you cannot point to a particular position in the sky. Okay. So instruments were almost ready, but there were a few things still to be checked. But over the weekend, they were stable enough that people left them running. And we all thought we would have to run for years. And this is what showed up on our monitors the Monday morning. So this is September 14th, 2015. This is the middle of the morning. This is what we call a time frequency plot. This is a way of displaying what is the energy which is deposited onto the instrument, the detector, coming from some signal as a function of time and a function of frequency. And you see that there is clearly a banana shape, both in the H1 means Hanford instrument and L1 means Livingston instrument. And you think, well, this is kind of silly. And in fact, the time here, I should stress the scale, this is milliseconds. Okay, so this is each interval here is 20 milliseconds. And in fact, there are tons of these things. But this is not quite the same as everything else, because to the trained eye, this is called the Chirp. Okay, this is what came out on the New Yorker the day after the detection was announced. So the two birds saying, was that you? I just heard it now, or was it two black holes colliding? So why is it called the Chirp? So I'm going to play, unfortunately, the Chirp. So the idea is, and I'm going to play it in a second. So this is again the same plot. The idea is that there is going to be a signal that is arriving. It enters the bandwidth of the instrument, which is around 20 hertz. And the intensity and pitch of the signal increases rapidly to some higher frequency, and then it disappears. And LIGO is really sensitive to a frequency band, which is the audio frequency band. Okay, so one can convert what is recorded by LIGO into an audio file. Okay, here the pitch has been increased because for people old like me, we cannot quite hear all the frequencies, and so here it goes. If I can, sorry. So this is really nothing terribly exciting. Okay, it's rather pathetic. However, okay, so now what I'm doing here, that was the time frequency representative. What I'm plotting here is as a function of time, the gray, very noisy line is the data that are actually recorded from the two instruments. This is the Livingston instrument, and this is the Hanford instrument. On top, you have reconstructed what is the signal that we measured that gave you this particular chirp-like signal. It's a silly wiggle, okay? It's a little sinusoid. So I'm going to tell you what this wiggle means. So every two of these cycles is one orbit of a binary system, okay? And this is a particularly interesting binary system because it's composed of two black holes. One black hole is about 35 solar masses. The other black hole is about 29 solar masses. Now, these are objects roughly, balls of around 50 kilometers, but that have been packed with 50 times or 30 times or 29 times the mass of the sun. These two black holes are roughly, when the signal enters the band of the instrument, at a separation of about 1,000 kilometers, which is the size of the UK, okay? They are moving around each other at about a third of the speed of light. This means that they do about 100 orbits in 1 second, which is, the kitchen mixer you have at home. They orbit around each other every two of these cycles for about 4 times. And as they move around each other, they are losing energy because they are radiating gravitational waves. Okay? By the time they reach this peak, they have emitted about the equivalent of 3 solar masses, 3 times the mass of the sun in gravitational waves. Okay, 3 times the mass of the sun in energy is more light, is more energy that is emitted in light by all the stars in all the galaxies in the entire universe. Okay? Now, nobody saw a flash of light, okay, because all this energy has been pumped into this fabric of the space-time. This traveled about 1 billion years from when it was generated by these two black holes that are racing around each other, on this racetrack that is produced by general relativity and gravity. Gravitational waves travel about 1 billion years that morning of the 14th of September, they enter the solar system, and then they hit the Livingston instrument first, and about 7 milliseconds later, the Hanford observatory. In fact, if you shift these two data sets by about 7 milliseconds, they will line up perfectly. And this scale here is, is what is the amplitude, and you'll see a number 10 to the minus 21, which is a very, very small number. So this is the observation of gravitational waves produced by the merger of a binary system of two black holes of about 30 solar masses. So this is great. It's about 100 years, or almost exactly 100 years after Einstein predicted gravitational waves, and predicted gravitational waves were not observables. So now you may say, well, great, wonderful, we have observed gravitational waves. Now we can nuke the place and move on and do other physics. But really, I mean, at least for people like me, when I got interested in gravitational waves, the idea was not really to confirm Einstein's theory of general relativity, but having a new way of looking at the universe. In fact, we observe gravitational waves, and with this observation, immediately, we have discovered a black hole binary system that we have never observed before. And actually, black holes of around 30 solar masses that we didn't know they existed. So this is a new way of doing astronomy. So in fact, now we know that somewhere in the universe, every 15 minutes, two black holes roughly of this kind will smash into each other and merge. And one of the big questions is, well, the universe seems to be a very efficient environment to create black holes. Remember, black holes are object of mathematical physics, and now we know the universe can create them very efficiently. In fact, these are different. We label the observation periods of these instruments as observing run. So observing run O1, O2, O3, A, and O3B. And this is the cumulative number of detection is about 90 of this system so far. This is a way of displaying what is the fraction of the universe we have observed. And I can assure you is a tiny fraction. Okay, it's just our neighborhood. So so some of the things that we've discovered. Okay, you cannot quite see this. Let's see if I can. I cannot. Okay, let's hope you can see it. So this is an event that was observed in 2019, May the 21st. This is a plot that shows what is the mass of the two objects that were observed. This is again a binary black hole. The interesting thing is that the primary mass is about 85 solar masses, and the secondary mass is about 65. Now, what's interesting about 85? Well, we think from standard stellar astrophysics, we cannot form a black hole of this mass. The idea is, black holes of tens of solar masses are coming from massive stars. Massive stars, live like James Dean. They live fast and die young. Okay. However, if the mass of the star that has will end up dying by exploding is too massive in the collapse, there is an effect known as pairing stability that blows up completely the star. Nothing is left. And this was considered to prevent the production of black holes about 50 solar masses. and now there is one here, 85 solar masses. So there are other mechanisms, other factories that work in a different way to produce these black holes. Here is a new discovery from these observations. And so these are again the two masses. One is a black hole, about 8, 10. So there are 3 events here, solar masses. You will see here that the mass, if you can see it, of the other object is somewhere between 1 and 2.5 or so solar masses. This is a failed black hole. It's called a neutron star. And a neutron star is a gigantic nucleus, almost entirely of neutrons, that has the mass of about 1.5 times the mass of the sun, and is about 10 kilometers in radius. And now we know, as we expected theoretically, but never being able to confirm it, the neutron star black hole system exists. Probably the most exciting event after the first detection is an event involving the collision of 2 neutron stars. So this is a binary system consisting of 2 neutron stars. It's of the same kind of 2 black holes, but now these are not black holes, are stars. There is a lot of material that you can take and you are smashing into each other and can fly apart. I'm going to skip this. And I'm going to go back to the the mid-60s. In the mid-60s, the US started to put in orbit a lot of gamma ray detectors. And the reason was that they were concerned that the Soviet Union was doing nuclear tests in space. And they put several of these satellites in orbit, and then they had almost instantaneously a heart attack because they started to see gamma ray bursts, gamma ray explosions all across the sky. This is you cannot see, it's covered by my zoom details here, but this is a report of 1976. So clearly people realized that these weren't, nuclear tests in space. The thing you can see is that this is an isotropic distribution. Clearly, it's got to be from an astrophysical source. And these gamma ray bursts have been one of the very fascinating aspects of astronomy and relativistic astrophysics. They've been, there are 2 classes, the long and the short one. The long ones are due to explosion of stars. The short ones, bursts that last for less than 2 seconds, what the engine was had been a mystery for a very long time. And people conjectured that this collision of 2 neutron stars could be the engine. So LIGO in 2017 observed this signal here of the collision of these 2 neutron stars in gravitational waves. There were gamma ray observers, instruments, in orbit at that time, Fermi and Integral. This is the time at which the 2 neutron stars merge according to the gravitational wave observation, and 1.9 seconds or thereabout, there is a flash of gamma ray bursts that is observed by these instruments. Now, these detections were done almost in real time. So this is noon, around noon, in Europe, in the middle of the summer 2017. And people realized that there is a collision of 2 neutron stars followed within a few seconds by a burst of gamma rays. Okay, because this was done in almost real time, people these instruments do not, they are not pointing instruments. They reconstruct the position in the sky through essentially time delays. This is the area where LIGO and Virgo estimated the source of gravitational waves was. And this lie very nicely on top of the area where the gamma ray burst was coming from. Now, it's the beginning, this sky map that says there is a signal both in gravitational waves and in gamma rays coming essentially from the same part of the sky. And the same part of the sky had an area which was about 150 times larger than the full moon. So they said, maybe it's the same thing. So it's the afternoon here. The sun is setting in Europe, but there is going to set in a few hours in a place where you have the best telescopes in the world, which is Chile. And in fact, you could have run essentially every single observatory in the world that afternoon. They were all pointing at this patch in the sky. And surely enough, in the middle of the night, about 11 hours later, this is a nearby galaxy observed 20 days before, and 11 hours after this gamma ray burst, there is a little dot in optical appearing. And actually, and it turns out this is a gigantic nuclear explosion. Okay, you take 1.5 mass of the sun made of neutrons, another 1.5 mass solar masses. You smash them against each other at 1/3 of the speed of light, and this is a cosmic firework. So it's seen in gamma ray, and then it's seen in optical, and over the course of the days and months, then it's seen in X-ray, in radio, across the entire electromagnetic spectrum. And is, okay, people call this as the birth of multi-messenger astronomy. I don't know whether that's a nice definition. It's a fantastic piece of observation. So there are a number of reasons why this is important. Well, for people doing relativistic astrophysics, this solves a mystery in relativistic astrophysics. What is the engine behind gamma ray bursts? Well, the engine behind at least some gamma ray bursts, this one, for example, is the collision of two neutron stars. There is another interesting point, which has to do with actually producing all the elements in the universe. It's just over 150 years since Mendeleev put together the periodic table. Now, we know the universe started from hydrogen, 3/4 of hydrogen, and helium, about 1/4, and nothing else. And then you have to populate the entire periodic table. And we know what does it. Well, it's stars. Stars synthesize all the elements, but up to a limit, because we know that, from hydrogen, you do helium, and then you move on your periodic table until it's not energetically favorable to produce heavier and heavier elements beyond iron. And so the question is, what makes all these heavier elements? And well, these are cosmic explosions in supernova, etc. But there is a problem in forming elements like, for example, gold and platinum. And was thought that, well, the theory goes that you really need extremely neutron-rich environment to have processes that are called R processes in order to create, for example, gold and platinum. And collision of neutron stars would be the ideal one. In fact, from all these observations across the entire spectrum, people were able to reconstruct that about 100 times the mass of the Earth was created in gold. So this is a way these events, populate the entire periodic table. All this material gets scattered into the interstellar medium. Then it starts to form the protoplanetary disk. It forms planets. And then at some point, a civilization comes in. And then we can mine these mines and have, I don't know, jewels and wedding rings and so on. So this is, just to show you, it's a simulation. This is the simulation of what happens to the elements during one of these collisions. This is the number of electrons, and this is the number of neutrons. The simulation is set up so that you start from typical conditions here up to about iron, nickel, and so on. And you will see, I'll run it. You will see that very quickly you produce elements with a lot of neutrons, and all of a sudden, boom, they sit all here in a stable state. And it lasts about 3 seconds, the entire thing. I mean, longer in the video, but that's what happens when you have this. Okay, this is through Zoom, so it's not terribly good. But as you can see, you propagate all very rich in neutrons, and now all of a sudden the neutrons decay, and they all go and form all the stable elements that we have for one conditions, okay? So these are the production, the cosmic production sites of these elements. Okay, I'll finish quickly. So what happens next? First, the instruments are going to be, improved continuously. We're going to start running again at the end of the year, and with better sensitivity. And this improvement will carry on and on and on. But at some point, and these are the design studies to get to the next generation of instruments, once in the 2030s, one wants to build instruments much larger. So this is a 10-kilometer underground cryogenic instrument, which is called Einstein telescope, that Europe hopes to build somewhere in Europe in the next decade. Similarly, in the US, a concept where you do a 40-kilometer interferometer is being developed. So they will allow us to see the entire, well, most of the universe. However, all these interferometers sitting on the ground here are limited to the fact that really the ground shake and there are masses like air moving, what is called Newtonian gravity gradients, meaning we cannot observe events that happen on time scales longer than, let's say, a second. And we would like, as we do in electromagnetic astronomy, to look at different wavelengths, okay, different time scales. So we need to go in space. And there are two ways of doing it. So one is to use pulsars that are extremely, there are neutron stars with that send us radio beams that are extremely stable, and we can observe down to the nanohertz region. So using a sort of galactic gravitational wave instrument, and we can go after, for example, the signals produced by the supermassive black holes at the center of galaxies. And in fact, there are some hints that these, sort of instruments may start to seeing some signal. The other one is to build a purposely designed instrument. This is in space, and this is called LISA. So this is to study, well, essentially to see the entire universe, the entire black holes that are at the center of galaxies in the universe. So this is a gigantic, if you want, LIGO. Instead of being 4 kilometers, these are 2.5 million kilometers. This has been approved by ESA. It's called the Laser Interferometer Space Antenna. We are now in phase B1, so in the formulation phase, and the hope is to fly this instrument hopefully before I die, so in 2034. What is the ultimate, what is the holy grail? Well, I'm sure different people will have different ideas. So this is, in many respects, the earliest picture we have of the universe. This is the cosmic microwave background. These are the photons that were emitted from that emerged from the Big Bang. The contrast in temperature is 1 part in 100,000. Okay, so it's not really hot and cold spots. They are almost all at the same chilling temperature of 2.73 Kelvin. But this is the relic of the Big Bang. The problem is that photons interact with all the photons around, and this picture that we managed to capture through, a fantastic achievement in technology was emitted when the universe was 300,000 years old. And the universe is opaque. Fundamentally, we cannot go past this curtain with the photons. But we can with gravitational waves. So there is another explosion, collision that happened at the, well, quote unquote, I'll fail the cosmology course, but at the beginning. Okay, so the Big Bang. And the universe is completely transparent to gravitational waves. And so in principle, with gravitational, there is an equivalent in gravitational waves of the cosmic microwave background. There is a cosmic gravitational wave background that would allow us to see the very, I don't know, the universe when it was a billionth of a billionth of a billionth of a billionth of a second old, what people call inflation, and really nobody knows what it is. So I'm sure I'll be dead by that point. But so this is I think this is the ultimate prize. So I think this is, we really don't know what we are going to discover next. And this is the beginning of, I think, really a new era of doing astronomy. And I'm sure fundamental physics and cosmology and nuclear physics and many other things. So I'll leave you with a letter from Feynman, if I can move this, that tells you that he wrote to his wife when he went to the very first conference on gravitation in 1962. That essentially says never do anything to do with gravity or general relativity. And I'm so glad he was wrong. Okay, I'll stop here. Really need to move this.
Nick, one of the microphones. Alberto, that was a brilliant talk. It absolutely caught the detail and the excitement and the potential. So thank you very much. I'm sure there will be some questions. I'll get my tablet shortly, but I can see a hand going up at the back.
I want to move this thing.
Something lurking around
the
screen.
It's really is the Zoom link, the Zoom control panel that I couldn't really move.
It irritated you much more than it did us. Don't worry.
Yeah, we didn't see it.
Yes. Yeah.
I'm not sure.
Okay. Let's take the question.
Yeah, I don't know whether it's a fair question to ask because I'm not sure it's your field, but I'm intrigued that they built a LIGO in Italy because that must be an incredibly noisy, tectonically noisy in every other respect. So do you have a sense in how you get these things to work practically?
Okay, you mean?
Do they? I mean, do they run continually, or
are
you forever resetting?
So now you said you are that you're surprised that they built a an instrument, one of these laser interferometers in Italy, because the site is not as quiet as the others in the US. So it's a fair point. Indeed, is not as quiet as the other one. In fact, the Virgo site is sinking a few millimeters per year. But Virgo, okay, but you know, it's a compromise between the perfect place and the place where you have the money to build something which is good enough. Okay, but so the Virgo instrument was the design really was based on a particularly clever suspension system that they designed, is called the super attenuator. Okay, but it's a particularly clever way of suspending the test masses and making it as stable as possible. That clearly has demonstrated that it's good enough. But I take your point. But I applied for a job at Virgo and didn't get it. So. So I shouldn't comment on.
So one of the sort of fascinating things that comes through is that it would seem that some of the commitments as to what the specification of LIGO and Virgo had to be would have been fixed before you knew what it was you were going to observe, or is that okay? I mean, for example, I mean the fact that the instrument works in the audio range, and it turns out there were objects that perform there, or was that all quite well understood?
So I think it was sufficiently well understood.
Yes,
meaning. So it was clear that one had to go to look for, astrophysical relativistic objects. Now, black holes are the ideal object, but people, okay, Einstein had, and Schwarzschild and Kerr, etc., had predicted black holes, but having the certainty they were there, well, people didn't have it, but they knew there were neutron stars. And they knew they were in binaries, and they did before building these instruments. And they did the calculations, and they, from the systems that were known from radio astronomy, they computed roughly what the event rate of this collision would be, and therefore what the sensitivity level that was needed.
Okay, so it was the binary neutron stars.
The binary,
and they were known about quite a long time ago, from the 1980s or before.
Oh, then. Before. So yes. The 70s, neutron stars were discovered. Isolated neutron stars were famously discovered here.
Yes.
So Tony Hewish and Jocelyn Bell in 67, 68. I don't remember exactly. And then soon after, in 1973, Hulse and Taylor discovered a binary of neutron stars that would merge, and actually that's very important. They got the Nobel Prize because, amongst the other things, the orbital separation of that binary shrinks due to gravitational wave emission. But they saw one of the systems, and you can compute that this system would merge in an ample time.
So that was enough to.
That was absolutely. That was that was the. There was a system there, and we thought from stellar evolution we would form these systems, and that drove broadly the design and the target sensitivity.
Thank you. There's a question across the way.
So sort of following on from that, you showed the graph or the sort of timeline of where future sensors are going to be moving to get at sort of lower hertz signals. Yeah. Lots of them, or sort of all of them, seem to be based on just making the baseline longer. And then you end up right at the end looking for something which can see through the cosmic microwave background. Now, I don't know if this is a bit unfair, given you said you think you'd be dead before you get to that point. I think I probably will be too. But are there any thoughts on what that sort of sensor might look like?
Are you specifically asking about looking for the background of gravitational waves from the early universe. Is that your question?
Yes.
Yeah. Okay. So first, to be totally fair, surely there are experts in the audience. There is a technique which is called, by looking at the polarization of the cosmic microwave background, to indirectly see a signature produced by gravitational waves. And maybe people will, you know, if you've heard the Bison story, etc., people will get there soon, but who knows? So in terms of the cosmic, directly with one of these instruments, the background from the early universe. So we have roughly an idea of how large it can be, you know, what is the maximum amplitude. Although there could be all sorts of exotic physics. But anyway, there is a target. If you try to hit that target, you know, with your dream instrument, you discover that the universe, it's such as, you know, high sensitivity, the waves are so weak that every astrophysical source become very loud. So now you find you have the same problem that all the astronomers have, that there is all this foreground. Okay, and this is fantastic. Okay, but actually it's a problem for you to have to see all the way back to the early universe. So it seems right now then there is only a window in frequency that maybe is clean enough. And this is a window between 0.1 hertz and 1 hertz. And this is observable only from the sky. But the instruments that are there, LISA and so on, are at too low frequency. So a new generation of instruments need to be put there. Does it address your question?
Yeah, it gets it. No. Yeah, it gets at some of the challenges.
But you need phenomenal lasers, stability of masses, inertia. I mean, but a lot of fun for experimental physicists.
Yeah, it is spectacular. I mean, and that point that the technologies that had to be available were probably not available when the commitment to get the project going was made. It's an amazing story.
It is. I think, yeah, there are these stories about Ray Wise, who then went on to win the Nobel Prize, that is sketched on his blackboard at MIT, roughly what is the sensitivity curve, and said, we need to control this noise source at this level, this level, this level. So let's get to work to develop this technology. Yeah. Cool.
Thank you for a super talk. I'm just thinking about the layout of LIGO in the north west of the States and the southeast of the States. You've got an x-axis and a y-axis, but there's no z-axis because you can't go down into the Earth.
Yep.
So are the signals from the two, how are they laid out? The ones on the two corners of the States? I mean, if one is north and one is west, are the other ones the same, or are they sort of northeast and southwest or something?
So you are asking about what is the...
Oh, it's on there, is it actually?
So they are essentially, the two LIGOs are, the two Ls are essentially parallel. Okay? They are essentially parallel. Okay. And that was done for a reason. Because you maximize the sensitivity of the instruments.
It looks on there as if they're at 45 degrees to each other? No.
No, no, they are almost almost exactly.
Oh, okay. So they can corroborate each other.
Yeah, so you get the
and then the one in Italy, for example.
The one in Italy is rotated by almost 45 degrees with respect to
around the Earth, so that tends to give you a bit of a z-axis, does it?
That tends to, yes, that tends to give sensitivity to the polarization of the waves and therefore also to the direction in the sky.
Yes,
you really need three. So they work like GPS, is by monitoring the delay in the arrival times. So you need at least three instruments.
Yes.
There is then a degeneracy north pole versus south pole, but it's and then you would like them ideally rotated by 45 degrees. And the reason is that gravitational waves are quadrupolar, and therefore the two polarization are offset by 45 degrees.
Thank you.
But what we would like is many, many instruments, all with different orientations.
Many is more than 3.
At least 4. So now, again, to be complete, so I've missed out something important, which is now Japan has an instrument called Kagra in the Kamioka mine, where the Super Kamiokande is. So this is the 4th instrument that is just, I mean, they are behind in terms of funding. Okay, fine. But now they are catching up. The sensitivity is much worse than the LIGO Virgo instruments, simply because they had to start later. But the idea is that in a few years, they will reach a sensitivity which is competitive with LIGO and Virgo. And the great thing is that they will do, the idea is to do the instrument cryogenic. And this is one of the big next leap in sensitivity, because for the future, people want to cool down all the test masses because of the thermal noise.
Sounds as bad as the Large Hadron Collider with all this liquid helium. Yes.
Oh yeah. Absolutely. I mean, this is yes. Yeah.
Another question.
Thanks for the great talk. Early on in the talk, you sort of made a slightly almost philosophical point about the universe, I paraphrase, being sort of awash with gravitational waves, and this is how it sort of communicated information or mass or the existence, I suppose, of objects throughout space-time. And that set me back in part 1A physics. I recall a thought experiment called Newton's water bucket. I don't know if you know this. So the idea is that you have a bucket of water and you're stood at the North Pole, and the meniscus on the bucket of water will follow a parabola. But the philosophical question is, how does the Earth, or how does the bucket know that it's rotating? And I seem to think the answer was a hand waving thing. Oh, it's the distant stars that provide the frame of reference. And so I was just wondering whether you're...
Okay. Probably is not good thinking on 2 feet after several glasses of wine. But so that was, that was a Newtonian experiment. This is terrible. I'm not familiar with the Newton bucket. So what's the experiment again?
Well, if you stood at the North Pole with a bucket of water, the surface of the water would be a parabola because of the Earth's rotation. So basically,
because of the Earth rotation.
So how does the Earth know it's rotating? How does it know it's rotating?
Okay.
And I was just wondering whether your idea of the distance.
But you see the Earth rotation, that is not an inertial system. The Earth that is rotating is not an inertial system. So I understand, so my philosophical point, I didn't want to make a philosophical point. The only thing I wanted to say at that point was that gravitational waves are a channel of information of gravity. That's the only thing I wanted to say for that specific point.
I have a question.
Sure.
If you have 2 black holes orbiting, or 2 neutron stars orbiting one another, and they merge and generate the waves, are the waves directional? If it's rotating this way, do the other waves stronger in the equatorial? Planes?
So there is, so it's kind of complicated, depends exactly on the spins, but the waves are directional. And in fact, they carry linear momentum, which means that the remnant of the 2 objects will recoil, for just conservation of linear momentum. And in fact, it has been, there are hints about supermassive black holes that are displaced from the center of the galaxies. And people have used this to argue that these black holes are the remnant of a merger of two previous black holes, and the recoil, because gravitational waves are directional, then has displaced them.
So that could mean that there are even more mergers in the sky than you're detecting.
So that number, that rough number, several per hour, is only for this class of black holes,
Yeah.
you know, tens of solar masses.
Yeah.
The monster at the center of galaxies, who knows? And that's one of the targets for the future.
Okay, final question. Great.
So it's a question about the mechanics of the interferometer itself.
Okay.
So my understanding is that the laser beam reflects along each arm multiple times before it comes out and merges back. But does it matter if you're getting a different number of reflections on one arm to another for a particular photon pair?
Okay, so the in reality, the arms. So the schematics I showed, where it is? No, it's before this one. It's a simple Murchison. This one is in the way. I really didn't want to start this. So the idea is the real instrument actually is not done in this way. There is another mirror here and another mirror there. So people create what is called an optical cavity that is, that is set up exactly to be a cavity that resonates at that particular frequency. So the idea is that the light is stored for a sufficiently long time so that the effect of the waves doesn't cancel out, because you are essentially multiplying the length of your instrument by the number of quote unquote bounces. And you maximize that effect. And probably haven't addressed completely the question.
Is that like a sort of Fabry-Perot?
Yeah, exactly. Yeah. And exactly, it's a Fabry-Perot cavity.
Yeah. Okay, I've just learned something. Thank you. Great. We've had a fantastic evening. It's just the talk we all wanted to come and listen to. Thank you.
Oh, thank you. You are
very
too
much
kind.
indeed.
Too kind.
Thank you.
Thank you so much. Thank you very much indeed.